So what we're trying to evaluate is what's happening in the course of this reaction. Okay? And the question goes through and says that ultimately this reaction doesn't go the way we would expect it to. When we run a standard reaction, we would expect that larger group, our hydrogen, to go to the position that has the most hydrogens, which is at that end of the double bond. Okay? However, that doesn't happen. So the question is ultimately asking, like, why does that not happen? Okay? The easiest way to evaluate that is to take a closer look at that reagent. Okay? So what we can do is draw that out. We get a hydrogen to our boron, and we've got our other hydrogens. Is that the correct Lewis structure for that compound? Okay, if you count everything out, boron comes in with 3 electrons, each hydrogen comes in with 1, 6 total electrons, they're all there. What's the hybridization of that boron?
sp2.
sp2, which means MTP orbital. Okay. What can we put into that MTP orbital? Electrons. So when we previously put hydrogen onto our carbon, okay, when we did that first step and we said we put a hydrogen at that position, why were we putting hydrogen there? Hydrogen's coming in as what charge? Positive. So what charge is building at that position?
Partial negative.
A partial negative charge. Okay. Well, we just went through and said that our boron has an MTP orbital. So what can we put in that MTP orbital? Electrons. So let's take the electrons of our pi bond and let's put them into that p orbital. What's the result? The electrons come out. Boron's now got too many electrons around it, so it wants to scare some electrons away. The only thing we've really got would be the hydrogens, okay? Except now they wouldn't be just hydrogen. Remember, boron has too many electrons around it, so it's not a hydrogen that comes out, but hydrogen with electrons. Hydrogen, remember, or hydride, is really, really, really unstable, so it needs to find something to stabilize as fast as possible. Okay? So if we're generating a very negative hydrogen, okay, this hydrogen becomes very, very negative, we need to give it a positive somewhere. Okay? Is there a positive building very close by?
On the other side of the pi bond.
We drew out our resonance for this. We got a negative charge there and a positive charge on the other carbon. So what ends up happening is our pi bond comes out, reacts with the boron, and then the electrons in hydrogen-carbon bond immediately go back to the positive charge on our carbon. The result is that we end up putting hydrogen in our more substituted position. So it appears to be anti to everything we've looked at. When in actuality, it really isn't anti, we just had different positives and negatives. We're used to seeing hydrogen as a positive. We add hydrogen to a boron structure, boron is so low on electronegativity that hydrogen can take the electrons away, and we end up getting that hydride instead of hydrogen ion. So we're still putting the most positive atom at the most negative position. So it's the exact same as we've learned before, we just changed the symbols. Okay? Does that make sense? Any other questions about it?
So do you want anything besides, because you want us to explain it, do you just want us to show what we showed here? Or is kind of what you showed, or what do you want beyond that?
That's it. Showing this would be perfect.
Okay.
And what is major, minor? What's the...
Major means that we're getting more of one. That's why it's the major product. It's in the larger concentration. Minor just means it's lower concentration. Depending on major and minor, we may see differing amounts. So, didn't it say major? Yeah. Major just means that there's a lot more of this compound than there is of the other one.
So if you had to choose between them, you would always use this one.
You would pick the major. Because that's the more likely product to actually occur.
Okay, so you're saying the hydrogen goes here, goes negative, and then the Br or BH goes down here. Okay.